Let's talk about chemical bonding, ionic and covalent. We'll go over some general concepts here. In the ionic bond, electrons are transferred. They're physically moved from one atom to another, or perhaps one ion to another. Here you see a sodium atom and a chlorine atom. The sodium atom has one electron in its valence shell. It's a 3s1 if you're interested. And that electron can be transferred to the valence shell of a chlorine atom, and the result, from this very active metal losing a valence electron to the highly electronegative chlorine atom, is you form a positive sodium ion and a negative chloride ion. So you've got a cation and an anion, and they, of course, positive and negative, attract each other. The formation of ionic bonds in this way is always exothermic. Looking at this diagram, you see a Bunsen burner down on the bottom here heating sodium chloride, and the sodium chloride is melting. This is very hot. This is well over 1,000 degrees Celsius. You also see a DC battery, some sort of power source, direct current, pumping electrons through the right-hand electrode, and the electrons are doing a chemical reaction here and here, but the point is that the molten sodium chloride is actually able to conduct electricity, whereas solid sodium chloride cannot. These ionic compounds, if they dissolve in water, can also conduct electricity that way because the current is a matter of moving charged particles. Finally, all ionic compounds have a relatively high melting temperature. Coulomb's law states that the energy of interaction between a pair of ions is directly proportional to the product of their charges divided by the distance between their centers. This is not the same as the force. As you see here, this is the equation with the Coulomb's constant, 2.31 times 10 to the negative 19th joule nanometers. And this is the proportionality, showing that the direct proportionality is to the product of the two charges, and the reciprocal proportionality is to the radius. So as the radius increases, the energy goes down. This gives you a picture of representative elements from the periodic table and their relative sizes of the ion and the atom. The gray outline or sphere represents the size of the atom, and the colored, red for the cations and blue for the anions, the colored is the ion itself. So metallic ions are smaller than the atoms they come from, and non-metallic ions are larger than the atoms they come from. This is a representation of a sodium chloride crystal lattice. You see the sodium ions, which are in red, and the chloride, which are in green. Ionic compounds form solids at ordinary room temperatures. They organize in a characteristic crystal lattice. The positive and negative ions will be alternating, as you see here. Overall, the charge on the crystal is a zero as a matter of course. Now let's talk about the enthalpy of reaction for forming an ionic compound. And we're going to use Hess's law to determine that. You'll recall that Hess tells us that if you can have a chemical process happening that the change in the enthalpy of it is the same no matter how you get from point A to point B. So we're going to add up some numbers to get that. So we're going to estimate the delta H of formation for sodium chloride, and of course that's from the pure elements, mole of sodium reacting with half a mole of chlorine gas to form the solid sodium chloride. We have to be very careful about how we do this, and we're going to use the table that you see here of lattice energy, ionization energy for sodium, electron affinity for chlorine, that's the energy that's gotten out when the chlorine grabs an electron and becomes negatively charged, the bond energy for chlorine gas, and the enthalpy of sublimation for sodium solid becoming sodium gas. And we're going to show you this pictorially as well with arrows. First of all, we have to take the solid sodium and turn it into a gas. And you see the 109 kilojoules per mole necessary for that. Then, of course, the sodium has to lose its valence electron, and that costs us 495 kilojoules. At the same time, we have to take care of the chlorine and break the chlorine molecule into chlorine atoms, and you can see the cost of that. All of these are endothermic processes, as you can see. Now, when the chlorine grabs an electron to become the chloride ion, we actually get back 349 kilojoules. And then when the sodium ions react with the chloride ions, sodium chloride solid is formed, giving us another 786 kilojoules. When all of these numbers are added up, we can get the overall reaction. But first of all, we need to see that we're going to get rid of everything except the reactants on the top of this page. So this gets rid of the gaseous sodium. This gets rid of the sodium ions in their gaseous state. We can see the electrons are gotten rid of at this step, and the chlorine atoms, the gaseous chlorine atoms, we've gotten rid of here. And finally, the chloride ions, gaseous, we get rid of here, leaving only the sodium, the chlorine gas, and the sodium chloride. And when we add those together, we get a total of negative 412 kilojoules per mole for the whole process. Now, what forces operate in a covalent bond? Well, we have both repulsive forces and attractive forces, because you'll recall in a covalent bond, sharing of electrons is the bond. First, you have electron-to-electron repulsive forces, and we see those outer shell electrons of the two atoms repelling each other. Second, we have proton-proton repulsive forces as the nuclei repel each other. So that pushes the atoms apart. But there's also electron-proton attractive forces. 1, 2, 3, 4 in this system that is holding the two atoms together. Now this gives us a diagram showing the distance between the hydrogen atoms in a covalent bonding situation versus the energy. So you've got separation distance, or internuclear distance in this case, on the horizontal axis and energy on the vertical. And we start off with the hydrogen atoms sufficiently far apart to have no interaction. We move them closer to each other. The atoms begin to interact. You can see that electron to the other nucleus attraction. You can see this mosquito graph here as the density of the electrons between the two nuclei increases. And here you have a hydrogen molecule has formed, and they're at the optimum separation distance, achieving the lowest overall energy of the system. If you push them closer together, at shorter separation distances, you have those repulsive forces starting to take over, and they increase the total energy. When you get it close enough here, towards here, you'll get a very, very clear pushing apart, they cannot stay that close together. The atoms then will oscillate around this optimum separation distance. You will get a quantized stretching effect, stretching and compression effect, almost like the oscillations around a spring. So let's look at bond length and energy. First of all, for carbon-to-carbon bonds, the single, the double, the triple, and we notice that as we go down towards the bottom, we're getting more bonds, but the bonds are getting shorter, from 154 to 120 picometers, and they're getting stronger as we're getting more bonds holding together. We then go to a carbon-oxygen bonds, a single or a double bond, and we see the same kind of thing happening. And finally, the carbon-to-nitrogen bonds, single, double, and triple. The bond length shortens, the bond energy increases. This is a tendency that you should remember. So let's see if we can, as one last thing, go from these bond energies to the enthalpy of reactions. And the bond energy, D, is the bond energy per mole of bonds. That the energy is required to break bonds and is given back when bonds are formed. Breaking bonds then always requires energy. Breaking bonds would be an endothermic process, and forming bonds will always release energy. That would be an exothermic process. Very much worth remembering. So let's show the delta H of reaction of methane. And of course, methane is reacting with 2 molecules of oxygen. And the first thing we do is we have to pull the atoms apart. Bond breakage then, the carbon-hydrogen and the oxygen, a total of 2,648 kilojoules per mole is needed. Then we form new bonds between the carbon and oxygen and between the hydrogen and oxygen. And the bond formation yields 3,466 kilojoules in the other direction. That's exothermic, of course. Now we'll leave it to you to calculate the net delta H of reaction for methane burning in oxygen gas from these two. And then we'll continue on our next video.